Hello, students. In the last class, we were discussing about the methods or techniques to increase the efficiency of the vapor power cycle. So we basically checked three different methods. The first one was by lowering the condenser pressure, we were able to increase the efficiency. Secondly, if we are going to increase the boiler pressure, then again there was an increase in the efficiency, or we can increase the efficiency by superheating the steam. So here in today's class, we are going to check uh, these effects numerically. In the start of chapter number 10, I solved one problem, and this is the problem that we solved in class in the start of this chapter. So this is our base question, and we will change the data from this question. So first of all, as we have already solved this question, so I'm just going with a quick review. So here, if you see, we have a steam power plant operating on a simple ideal Rankine cycle. So we have the simple ideal Rankine cycle. Steam enters the turbine at 3 megapascal and 350 degrees Celsius. So this is the turbine inlet condition, and is condensed in the condenser at a pressure of 75 kilopascal. So this is the condenser pressure. So we know two different pressures, the boiler pressure and the condenser pressure. And for an ideal Rankine cycle, we need only two pressures line. So determine the thermal efficiency of this cycle. So here we have the cycle where we have the pump, boiler, turbine, and condenser. At point number 1, we have the 75 kilopascal. At point number 2, after this pump, we have 3 megapascal. Then we have constant pressure heat addition, and we have 3 megapascal again, but we have the temperature of 350 degrees Celsius, so it means we are somewhere in this superheated region. Then this steam is going to expand in the turbine, and we are getting some work output. And this process is basically taking place at asymptotically, because the entropy remains constant. So S3 is equal to the S4, and then we have the 75 kilopascal. So with the help of S4, first we will check the state at point number 4, and then we will find the value of enthalpies at point number 4. So here we have the TS diagram for this cycle. With the point number 1, ideally it should be on saturated liquid line. So we have the point number 1 here. We have the point number 2 somewhere here at 3 megapascal. So we have isentropic compression. So we have a straight line. So S1 is equal to S2. Then we have 2 to 3, which is constant pressure heat addition. So we have to check the value of H2 and value of H3, and by subtracting H3 minus H2, like subtracting H2 from the H3, we will get the Q in. Then we have the isentropic process in the turbine, and then we can get what is H4, and then we have the simple formulas to calculate the Q in, Q out, W net, and then we can find the efficiency. So here we have the point number 1, which is at 75 kilopascal, and we have the saturated liquid. So here we have the state number 1, which is 75 kilopascal and saturated liquid. So H1 will be the HF at given pressure. So we have the value of 384.44 kilojoule per kilogram. Same way we can find the V1 as well. So V1 is VF, and we have the value of V1 here. We can check the T saturation as well at the temperature at 75 kilopascal, or the temperature at the inlet of the pump. At the state number 2, we know that we have the pressure of 3 megapascal, and also we know it's an isentropic compression in the pump. So basically, for pump, we can use this formula, which is the work pump in equal to V1, the specific volume at point number 1, and then we have the difference in the pressure. So we have V1, V2 minus V1, and when we will put the values here, we will get 3.03 kilojoule per kilogram. So this is the work input to the pump. Now this pump work input is also equal to H2 minus H1 in terms of enthalpy. So I can find the value of H2, which is the H2 will be equal to the work input plus H1, or H1 plus work input. So we will get around 387.47. So this is the value of H2. Now For a state number 3, we know that we have the 3 megapascal pressure and the temperature is 350 degrees Celsius. So we can check easily from the superheated table, and the values we are getting around 3116.1 kilojoule per kilogram for H3, the enthalpy, and the S3, the entropy is around 6.745 kilojoule per kilogram Kelvin. So we can check these values from table A6. Now, as we know that S3 and S4 are same because we have the isentropic expansion in the turbine, and at the end of the turbine we have the pressure of 75 kilopascal. So at 75 kilopascal, first of all we have to check the value of SF and SG. Right now we have the value of SF, which is around 1.2132 and SG is around 7.4558, and the given value or the S4 value is basically in between the SF and SG. So it's mean we have the liquid vapor mixture. So whenever we have the liquid vapor mixture, so we can easily check out the quality of the steam. So it will be simply S4 minus SF upon SFG or SG minus SF. So just by putting the values, we will get the X value or the quality value of the steam, and it comes to be around 0.886, so 88.6% quality. So when we know what is H4, sorry, X4, so we can easily find out the enthalpy value at state of 4. We have the pressures of 75 kilopascal, and we know it's a liquid vapor mixture, so we can easily check what is the HF value and what is the HG value. And by using the basic formula, which is H4 is equal to HF plus X HFG, we can easily calculate the value for H4, and it comes to be 2403 kilojoule per kilogram. So right now we have already calculated the enthalpies at state number 1, state 2, state 3, and state 4. So whenever we have the enthalpy values at all points, so we can easily calculate the Q in, Q out, and even W in and W out as well, or W net as well. So we have Q in, which is H3 minus H2. So we have the value of Q in equal to 2728.6, and Q out will be equal to H4 minus H1. So you will get 2018.6. So as we know that we have the thermal efficiency formula, which is W net upon Q in, or we can write down the formula like 1 minus Q out upon Q in. So we know what is Q out and we know what is Q in. So ultimately we will get the efficiency of 26%. So this is the efficiency of this simple ideal Rankine cycle, where we have 75 kilopascal condenser pressure and 3 megapascal at the boiler pressure. Now from here we can solve this question in this way as well. So we have H3 minus H4 for turbine output, and we have the W net, which is out minus N, the work output from the turbine minus the work input to the pump, and then we can check W net upon Q in, and you will get the same answer. Now from here we are going to check that either if we are going to increase the boiler pressure or decrease the condenser pressure, or if we are going to superheat the steam. So at the end, either we will get the increase in the efficiency or not. So here we have the problem number 7. So here if you see, we have the consider a steam power plant operating on the ideal Rankine cycle. Again we have the ideal Rankine cycle. The steam enters the turbine at 3 megapascal and 350 degrees Celsius. So we have the same data for the turbine inlet, and is considered in the condenser at a pressure of 10 kilopascal. Now in this case you can see we have decreases the pressure from 75 kilopascal to 10 kilopascal. So the pressure is reduced in the condenser. So first of all we have to check the thermal efficiency for this power plant. Now in part B, what we will do, we will find the thermal efficiency again. Now but in this case we have the steam is superheated to 600 degrees Celsius instead of 350. So we will maintain this pressure and this pressure, and we will change the superheating temperature, and then we will compare the result that either the efficiency is going to increase or not. And in the last part we will change the boiler pressure. So here the thermal efficiency determine the thermal efficiency if the boiler pressure is raised to 15 megapascal instead of 3 megapascal. We have raised up to 15 megapascal, while the turbine inlet temperature is maintained at 600 degrees Celsius. So we will compare with this data, or with this set of data. So we know we have the efficiency of 26 kilopascal, sorry 26 percent if the condenser pressure is 75 kilopascal and the boiler pressure is 3 megapascal and turbine entry is at 3 megapascal and 350 degrees Celsius. Now For this case, when we have the 3 megapascal and 350 degrees Celsius and 10 kilopascal, now we have 10 kilopascal. We have to solve the Rankine cycle in the same way as we solved in the previous question. So here, first of all, we have the TS diagram. So here we have 10 kilopascal here instead of 75 kilopascal. The rest is same. So at step number 1, we have 10 kilopascal. We have saturated liquid. We have saturated liquid at this point. Ideally, this point is always at saturated liquid line. So we have H1, which is HF at 10 kilopascal, and we will get 191.81, and V1 is equal to VF, and we are going to get 0.00101 at state number 1. For state number 2, we know that the pump work input is simply V1 P2 minus P1. So we can easily find out the pump work input, and in this case it's simply 3.02 kilojoule per kilogram. So we know what is the V1 value, and P2 and P1 are already given, which is 3 megapascal and 10 kilopascal. So when we know the pump work input, then we can easily calculate the H2, the enthalpy at point number 2, because the pump work input is also equal to H2 minus H1. So by doing this one and then rearranging the equation, so we will get H2, which is equal to H1 plus the work input to the pump. So ultimately we will get 194.83 kilojoule per kilogram, and this is the H2 value. So we know what is H1, we know what is H2. Now, for point number 3 or the state number 3, we have the 3 megapascal and we have a temperature of 350 degrees Celsius. So we can easily check the state number 3. So we will get H3, which is equal to 3116.1, and S3, which is 6.7450 kilojoule per kilogram Kelvin. Now, this is the state number 3 from superheated table, which is table A6. For state number 4, we always have to check the state first or the phase description. So as we know that S3 is equal to S4, and we have the 10 kilopascal at state number 4. So at state number 4, we have 10 kilopascal and S4 is equal to S3. So when we will check this one, the given value, when we will check the SF and SG, so you will find that S4 lies between SG and SF. So it's mean you will get the vapor liquid mixture at the turbine outlet. So it's mean we have to find the quality first. This is the same. We are basically following the same steps as we did in question number 1. So X4 will be S4 minus SF upon SFG. We know the value of SF, which is equal to S3. We know SF and SFG from the table, and we will get the the quality value of 0.8128. So around 81.28 percent quality. Here you can see the quality is decreased. Last time it was around 88%. So when you are going to decrease the condenser pressure, the the quality will also decrease, or the moisture contents are increased. Now, with the help of X4, and we know it's the saturated vapor mixture, so we can find the value of H4, the enthalpy. So H4 will be HF plus X4 HFG, and when now we will put the values, we will get the answer of 2136.1 kilojoule per kilogram. So we have H1, H2, H3, and H4. When we have all these values, so we can easily find out what is the Q in and the Q out, and even we can find out W in, W out, and W net as well, and then finally we can find the efficiency. So here if you see we have Q in and Q out. Q in is simply H3 minus H2, and you will get the answer of 2921.3, and for Q out you will get the answer of 1944.3 kilojoule per kilogram. So when we know the Q in and Q out, then we can find the efficiency, and it will be equal to 1 minus Q out upon Q in. So here we are getting the efficiency of 33.4. So remember the last part in the last question, basically we had the efficiency of 26%. Now we have decreased the condenser pressure, and you can see the efficiency is basically increased from 26 to 33.4%. So it is proved that by decreasing the condenser pressure, the efficiency will increase. So here you can see that the efficiency is basically increased from 22%, 26% to 33.4%. Also, we have changed the pressure from 75 to 10 kilopascal. At the same time, as I told you in the last slide, that there is an increase in the moisture content. Last In the last question, we had the moisture content of around 11.4% or the quality of 88.6%, but now the quality is reduced from 88.6 to 81.3. So it's mean the moisture contents increases from 11.4. 11.4 is basically 100 minus 88.6. So 11.4 to 18.7, so 100 minus 81.3. So quality is basically 81.3, but moisture contents are 18.7. So simply you have to subtract the quality from 1 or 100 value. So this is the first part where we have checked that by decreasing the condenser pressure, we can increase the efficiency. Now we have to perform the same calculation, but we have a new data set, and in the new data set, if you see here in part number B, we have to superheat the steam. So here, if you see in the part B, you have to find the thermal efficiency if the steam is superheated to 600 degrees Celsius instead of 350 degrees Celsius. So it's mean when we are going to check this one here, we have 10 kilopascal condenser pressure. We have 3 megapascal of the boiler pressure, but the turbine inlet condition is changed from 350 to 600 degrees Celsius. Basically, we have increased the temperature. So here, the point number one will be same because there is no change in state number one. It's simply 10 kilopascal, and we have the saturated liquid at point number one. There will be no change at point number 2 as well, because point number 2 is at 3 megapascal, and we have to check from the same formula, that is W pump in is equal to V1 P2 minus P1, and you will get the same answer as you got in part number A, and then you can find the H2 value as well, and it will be same. But only thing that is going to change is the value of H3. Because in the last part we had 3 megapascal and 350 degrees Celsius, so from a superheated table we got one value, but here we have 3 megapascal and the temperature is 600 degrees Celsius, so temperature is basically increased, so you will get different H3 value, and then you will get the different S3, the entropy and enthalpy. You will get the different enthalpy and entropy values, and based on the entropy value you will get a different entropy and enthalpy value at state number 4. So state number 1 and 2 remains same, but the state 4, 3 and 4 are changed by superheating. So I'm not going to solve about the state number 1 and 2. For state number 3, we have we have 3 megapascal and 600 degrees Celsius. So you will get the value of H3, which is equal to 3682.8 kilojoule per kilogram, and you will find S3. So you will get an answer of S3 at state number 3. So by putting S3 equal to S4, you have to first find the quality, because you will get the vapor liquid mixture. When you will find the quality by using X4 is equal to S4 minus SF upon SFG in terms of entropy, then you will get the quality of 0.915. So you can see here the quality is basically increased from 83, I think 83 or 82 to 91.5%. So moisture contents are decreased by superheating the steam. Then with the help of X4 we can find the enthalpy value, which will be equal to HF plus X HFG, and then you will get the value of H4, which is equal to 2380.3 kilojoule per kilogram. So by doing this we can find the enthalpies at different points. Ultimately, when we have the H1, H2, H3 and H4, so we can easily find out what is Q in and Q out, and here we will get the Q in, which will be equal to 3488 kilojoule per kilogram, and Q out will be equal to 2188.5. So here you can see the Q in and Q out are also changed, and then we can find the efficiency. So by doing this one, when you will solve, we will get the efficiency of the Rankine cycle around 37.3%. So efficiency is basically increased. So in this part, the efficiency is increased from 33.4 to 37.3%. So basically there is an increase if we are going to superheat the steam from 350 to 600 degrees Celsius. At the same time, you can see that the quality is also improved. Last time it was 81.3, and now we have 91.5. So basically, moisture contents are decreased from 18.7 to 8.5%. And normally, it is recommended that at the turbine outlet we have less moisture contents. Normally, we can allow up to like 90% of the quality. So it's recommended that the quality should be higher at the turbine outlet. Otherwise, as we discussed in the previous class, that there will be chance of erosion, corrosion, and then the blades will be damaged due to this erosion and corrosion. So here we can see that the efficiency is increased by superheating. Now, what we are going to do? We are going to increase the pressure now in part number C. So this is the condition. So we have 10 kilopascal for the condenser pressure. We have state number 1 here, but state number 2 is basically at 15 megapascal, and then we have T3 which is at 600 degrees Celsius. So we didn't change the superheat temperature, other than we have increased the boiler pressure. But due to the increase in the boiler pressure, ultimately you will get the higher value of at point number 3. So here the state number 1 is the same. There is no change in point number 1 because this is the saturated liquid. This is the state number 1 is at saturated liquid line, and the pressure is 10 kilopascal. So you will get the same value of H1 and V1 at state number 1. But for the state number 2, we will get a different answer because now we have 15 megapascal. Last time it was 3 megapascal. Now we have 15 megapascal. So at state number 2, we will get W pump in, and it will be equal to V1, which is the same as we have calculated in the previous parts. But we have P2 minus P1, and here we have P2 which is 15 megapascal rather than 3 megapascal. So 15 megapascal minus 10 kilopascal and times V1. So we will get the different pump work input. So when we will get the different pump work input, then we can find the H2 value. So H2 value will be H1 plus the work input, and here you will get the H2 value of 206.95. Last time it was less than this one, so it's been the pump work is basically increased by increasing the boiler pressure. Again, at state number 3, we have the 15 megapascal and T3 which is 600 degrees Celsius. So from the superheated table, we can check the value of H3, and here we are getting the H3 value of 3583.1 kilojoule per kilogram. At the same time, we have to check what is the S3 value, because with the help of S3, we have to locate S4 or state number 4. So we will check the value of S3 at state number 3, and then at state number 4, we have the pressure of 10 kilopascal. So first we will compare the S4 value with SF and SG. You will find that S4 lies between SF and SG. So it's mean at state number 4 we will get the vapor liquid mixture. So whenever we have the vapor saturated mixture vapor saturated liquid vapor mixture, so we have to find the quality first. We have the formula for the quality, which is X4 is equal to S4 minus SF upon SFG. When you will solve this one, you will get the quality of 0.804. So we have the quality of 0.804. So it's been around 80.4% quality. Last time it was 91. So quality is decreased, or the moisture contents are basically increased. So when we have the X4 value, then with the help of the data from the stream table, we can find what is HF and HG at 10 kilopascal, and then with the help of simple formula, which is HF is equal to HFG, we can find the value of H4, and you will get the answer of H4, which is equal to 2115.3 kilojoule per kilogram. So again, we have H3, H1, H2, H3, H4, and we have the basic formulas of Q in, Q out. So we will get the answer of Q in and Q out. So you can see the Q in and Q out are also changed, and then we can find the efficiency. Here we can see the efficiency value is around 0.43 or 43 percent. So the efficiency is increased. The pump work is also increased. You can check the Q in and Q out value as well. So Q out, if you see Q out, so I think it's basically decreased. Last time the Q value was different, and now we have Q out, which is 1923. So we can check here. We have 1923 here, and here we had 2188.5. So it's mean Q out is decreased. What about Q in? Last time it was 3488, but we had the pressure of 3 megapascal, so we cannot compare directly. But right now, this one Q out is basically decreased. So we have the Q out, which is 1923.5, and we have the Q in, which is 3376.2. So the efficiency will be around 43%. So here we have got the increase in the efficiency from 37.3% to 43%. Because we have changed the pressure, or the boiler pressure, from 3 megapascal to 15 megapascal. But in both cases, we have maintained the inlet temperature at the turbine. So basically, maintain the temperature at the inlet of the turbine, and the temperature was around 600 degrees Celsius. At the same time, you can see the quality was decreased. Previously, it was 91.5, and now we are getting around 80.4, which is very less. And due to this one, we will get around like 20 or 19.6% of the moisture content at the turbine outlet. So this will create the problem. So when we are going to increase the boiler pressure, so it's also recommended to do some superheating, or we can perform the reheating. We will discuss about the reheating in the next lecture. Now here we have another question. If you see in this question, we have the network output and the thermal efficiency for the Carnot cycle, Carnot, and the simple ideal Rankine cycle with the steam as the working fluid are to be calculated and compared. So basically, we have to find the network output and the thermal efficiency. Now, what is the condition for these two cycles? First of all, we have the steam enters the turbine in both cases at 10 megapascal as saturated vapor. So steam is basically entering at 10 megapascal, and the phase description is basically saturated vapor. So it's been, we have the x value equal to 1 at the turbine inlet for both cases, and we have the condenser pressure of 20 kilopascal for both cases. Now in the Rankine cycle, the condenser exit state is saturated liquid, which is basically the ideal Rankine cycle, because the condenser exit, or the point number 1, state number 1, is basically at the saturated liquid line. And in the Carnot cycle, the boiler inlet state is saturated liquid. This is basically the difference between these two cycles, because when we're talking about the Rankine cycle, so the boiler inlet state is basically in compressed liquid region, while here when we are going to deal with the Carnot cycle, so boiler inlet state is saturated liquid. So we have to draw the case diagram for both cases as well, and we have to find the thermal efficiency and the work output, the net work output. So first of all, we are going to solve with the Rankine cycle. We have the ideal Rankine cycle. So we will get the TS diagram like this one. We have the state number 3, the turbine inlet at the given pressure, and we have the x value equal to 1. So we have at this we have the state number 3 at saturated vapor line, and we have this state number 1, the condenser outlet, at the saturated liquid line, and this is the basic cycle for ideal Rankine cycle. So when we know the diagram and we know the data, we have the 10 megapascal and 20 kilopascal. So we have 20 kilopascal here, and we have 10 megapascal here. So rest is very easy, because we know we have to follow the same steps. So the first step is the state number 1. We have to find the enthalpy at state number 1. So it will be simply the H1 will be equal to HF at the given pressure. And right now we have the given pressure of 20 kilopascal. So we can find the value of H1 at state number 1. And at the same time, we have to check the value of V1 as well, because we have to find the H2, or we have to find the pumping work input. So H1 is simply HF at 20 kilopascal, and the value is around 251.52 kilojoule per kilogram, and the V1 is simply VF at 20 kilopascal. So our answer is 0.001017 meter cube per kg. So if we have the enthalpy and the volume at state number 1, so we can easily check out the work input to the pump with the formula, which is V1 times P2 minus P1. So we can get the pump work input, and the answer will be around 10.15 kilojoule per kilogram. So if we know what is the work pump input, so we can easily find out the value of H2, because the pump work input is also equal to H2 minus H1. So H2 will be H1 plus the pump work input. So it will be 251.42 plus 10.15, and then we will get 261.57. So this is the H2 value. At state number 3, right now in this question we have the saturated vapor. So it's mean we will check the value of H3, which is equal to Hg at the given pressure. So we have 10 megapascal and X3 is 1. So H3 is basically Hg at 3 megapascal. So we are getting 2725.5 kilojoule per kilogram. And the value of S3, the entropy is around 5.6159 kilojoule per kilogram Kelvin. So here we have to follow the same procedure again, because we have the S3. So we are going to say that the S4, the entropy at point number 4, is same as we have the S3. So S4 will be equal to 5.6159, and we have to check the values of SF and SG at 20 kilopascal, and you will find that the S3 or S4 lies between SF and SG. So it will be in vapor mixture region. So we have to find the quality value, which will be around X4. The formula is like simply X4 equal to S4 minus SF upon SFG, and we will get the answer of 0.6761. So around 67.61% quality at point number 4. So we can easily check what is the enthalpy at point number 4. So enthalpy will be equal to HF plus X HFG. So with the help of this one, we will get the H4 value, which is 1845.3 kilojoule per kilogram. So we have H1, H2, H3, and H4. We have to find the enthalpy, as well as we have to find the W net. So W net will be equal to either the turbine output minus the the turbine output minus the pump work input, or we can find the W net by simply equating Q in minus Q out, because in both cases you will get the same answer. So here the Q in is simply H3 minus H2, and we have H3 value of 2725.5 minus 261.57, and we are getting Q in is equal to 2463.9 kilojoule per kilogram, while Q out is simply H4 minus H1, and we will get 1594 kilojoule per kilogram. So what is W net? So W net is simply Q in minus Q out, and we will get around 869.9 kilojoule per kilogram. So this is the W net. So when we know what is W net, so we can easily find out the efficiency as well, because efficiency is either 1 minus Q out upon Q in, or the W net upon Q in. So in this case, when we will solve for the thermal efficiency, we will get the answer of 35.3 or 0.353. So 0.353 efficiency, or 35.3 efficiency for this Rankine cycle. Now we have to solve the same cycle. We have the same setup for the Carnot cycle as well. And the Carnot cycle, we have to change this portion, this one, because here we have state number 1 somewhere here at this saturated liquid line. But as mentioned in the question, that in Carnot cycle we have state number 2 at this point. We have this state number 2 at saturated liquid line. So we have to shift this state 2 from here to here. So if we have the Carnot cycle and we have the state somewhere here, so we know that the process 1 to 2 is isentropic process. So we will get a line from here to here. So 1 to 2 will be from here to here, like as you can see here in the diagram. So this is TS diagram for Carnot cycle. So we have 3 to 4, we have 1 to 2. So because we have state number 2 here, so then entropy at point 2 and point 1 is same. So we will get a straight line like this one. So state number 1 is not here. So now here again we have 10 megapascal at point number 3, and we have saturated vapor at point number 3. So we can easily calculate the value of H3. We can easily get the value from the table as well. Basically it's simply H3 is equal to Hg, as we did in this part. So we have H3, we have the P3 which is 10 megapascal, and we have the X3 which is 1. So we are getting H3 equal to, and H3 2725, and S3 equal to 5.615. So we will get the same answer for the Carnot cycle, because state number 3 is same. Scenario number 4 is also same because we have this one, so we will get the same value of H3 and H4 when we are going to solve for Carnot cycle. So H3 and H4 are same, but we have H2 and H1, they are basically slightly different because H1 is not here and H2 is not here. So we have H1 and H2, and we have to calculate these values because now we have point number 2 at the saturated liquid line. So here, as we know that the temperature remains constant during this process, so either we can get the values from the table. So here we will get here we will get the H2 value, which is around 1407 based on the temperature of 311, which is the saturation temperature. So we can get the value from the saturation temperature. Here, if you see, we can check the H2 value with the help of either 10 megapascal, or we can even check the T3 because T2 and T3 will be same. So we have the sorry, we have the 10 megapascal, so H3 is simply 2725, and at the same P3, which is 10 megapascal, we can check the H2 as well, and H2 will be HF. So if we go to the stream table here, so this is the table A5, sorry, this is table A5, and this is the 10 megapascal. So you can see here we have Hg value, sorry, this one, the HF value of 1407, and we have the saturation temperature of 311, and we have the Hg value of 2725. So here, as you can see, sorry, as you can see, we have the H3 at 10 megapascal as Hg. So we have 2725.5 kilojoule per kilogram, and we have the H2, and it will be equal to HF at 10 megapascal. So we can easily calculate with the help of 10 megapascal. This is slightly confusing, but still we can use with the help of for the temperature as well. So at the same point, we are going to check the S2 as well because we have to find the enthalpy at point number 1. The H3 and H4 are same as we calculated in the previous part, and H2 is from the HF at the given pressure. So when we'll check the entropy here, so we'll get S2, and this S2 will be SF. So it's simply 3.3603. So this is the entropy here at point number 2. So the entropy at point number 2 and the entropy at point number 1 both are same, and we know the pressure here is 20 kilopascal. So we have 20 kilopascal, and we have the S1 is equal to S2. So with the help of S1, we have to find what is X1 at point number 1. So it will be equal to 0.3574 at point number 1, and then we will calculate the value of H1 at point number 1. So it will be around 1093.9 kilojoule per kilogram because we have the point number 1 inside the dome other than at the cellular liquid line. Now we have H1, H2, H3 and H4. H3 and H4 are same as we calculated or we checked in previous part. So here we have the Q in and Q out. So Q in and Q out will be H3 minus H2 and H4 minus H1, and we will get 1317.7 for Q in, and we will get 751.4 for Q out, and for W net simply Q in minus Q out. So we are getting 575.4 kilojoule per kilogram. And when we are going to check the efficiency, so we will get 1 minus Q out upon Q in. So it will be around 0.430. So we are getting 43% efficiency when we are using the Carnot cycle, and here we are getting around around 35.3% efficiency. So we have different efficiencies even we are operating within the same pressure range or the temperature range, because in the Carnot cycle we have the same temperature, and here because the temperature in the boiler and the temperature in the condenser for both cases is basically same. So here today we have discussed about the Carnot cycle, Carnot cycle as well as the Rankine cycle, and we checked we confirmed the increase in the efficiency with the help of decreasing the condenser pressure or increasing the boiler pressure, or with the help of superheating. We also confirmed that the efficiency will increase. Now in the next class, we will discuss about another method, and this method is basically the reheating process. Because as we say in the case of increasing the boiler pressure, we checked that we had less quality of the steam at the turbine outlet, or we had more moisture content at the turbine outlet. So we can resolve this issue with the help of reheating. So what is the reheating? We will study in the next class. So thank you.